All right, here's my project. This is my immune responses to the Zaire Ebolavirus, and this is the immunology infectious disease cascade video. All right, so origin and history. There are many species of infection within the genus Ebolavirus. However, the main virus called Ebola is caused by the species Zaire Ebolavirus. The species of Ebolavirus, EBD, I will be discussing in this presentation is the Zaire Ebolavirus. Scientists do not know the exact origin story of EBD, but they believe it is animal-borne based on similar viruses, with bats or non-human primates being the most likely source. Infected animals carrying the virus can transmit it to other animals, like apes, monkeys, and humans. There are some other known species of EBD, but scientists do not know if it is able to infect humans or not. What we do know is that EBD was first discovered in 1976 near the Ebola River in what is now known as the Democratic Republic of Congo. Since then, the virus has been infecting people from time to time, leading to outbreaks in several African countries. This is just a picture of the Democratic Republic of Congo. And if you see my cursor on the screen, that is where the first Ebola outbreak occurred, near what they call Ebola River. They have another name for it too, but that's where it started. So there are two main symptoms a person gets with EBD, and they are called dry symptoms and wet symptoms. Symptoms can appear anywhere from 2 to 21 days, so an incubation period of 2 to 21 days after contact with the virus, with an average of 8 to 10 days. The illness typically starts with flu-like symptoms, such as fever, aches, and pains, and fatigue, which are known as dry symptoms. Other symptoms, such as diarrhea and vomiting, which are also known as wet symptoms, typically develop later. The most distinct symptom is its unexplained hemorrhaging, bruising, and bleeding. EBD is very rare due to the way it needs to transmit to infect people. The recovery from EBD depends on good supportive clinical care and the patient's immune response. There's also a lot of studies that show that survivors of EBD develop antibodies to provide protective immunity, making it significantly easier to fight a second infection. All right, so transmission. The virus spreads through direct contact, such as through broken skin, for example, or saliva, sweat, contaminated objects, body fluids, animals, and even through semen. Ebola virus can survive on dry surfaces, like doorknobs and countertops, for several hours. In body fluids like blood, the virus can survive up to several days at room temperature. It is important to use hospital-grade disinfectant to clean surfaces that may be contaminated with the virus. So speaking of mortality, according to the World Health Organization, the average Ebola virus case fatality rate is around 50%. Case fatality rates have varied from 25% to 90% in past outbreaks. That's kind of scary. All right, so starting with 5 activated immediate innate immunities, I'm going to start by talking about defensins. So defensins are a type of antimicrobial peptide that protect against pathogenic infections. Specifically, in this case of Ebola virus and other viruses, defensins inhibit viral replication of most viruses. There are many, many types of roles that defenses have. Surprisingly, there are both infection inhibiting and infection promoting mechanisms of defensins. So there's some controversy over whether people want to even recognize defensins as really helpful or not. Here, I'm going to talk to you about just a few mechanisms alpha defensins used to interfere with viral infections, such as Ebolavirus disease. We can see in this diagram, there are many routes a defensin can take during a viral infection, such as the Ebolavirus. A defensin can, number one, it can directly inactivate a virus. Number two, it can block interactions between the virus and the cell's receptor. Number three, it can block viral fusion into the cell or into the cell wall. And number four, it can inhibit nuclear import in viral transcription. So like, let's see, so defensin can, number one, directly inactivate a virus. So if I can get my cursor on the screen, so boom, here is an example. These are defensins here. So boom, it can go right to like HIV, for example, and it can actually just deactivate the virus sometimes. Or boom, number two, it can cause a disruption between the receptor and the virus. And then see, it's blocking it here from going into the cell wall. It can do that too. So just there's many purposes of antimicrobial peptides. All right. So for the second activated immediate innate immunity is the skin. The skin actually serves as a barrier to protect and separate our bodies from the pathogenic microbes of the environment. However, the skin offers many antimicrobial properties. Pathogens have ways of overcoming these protections. It's like in wrestling, there's always a counter to a counter to a counter to a counter. That's just going on in microbiology too. So the skin serves as a wall-like barrier that separates the inside of our body from the microbial enemies of the environment, and it provides a primary defense against infection. The layers of the skin, like the outer wall and secondary inner walls surrounding a medieval city, not only provide protection from external enemies, but also provide niches where normal flora, bacteria, and fungi can live and conduct business. So yeah, so the skin is essentially like a castle with walls around it, like a medieval city with walls around it. But as soon as it gets broken, as soon as there's an opening, like a cut, a scrape, inflammatory rash, cutaneous infection, autoimmune skin problems, the virus is going to get in, the virus is going to cause an infection, right? Any kind of skin damage whatsoever. And they can cause major damage, especially a virus such as Ebolavirus disease. If it gets through the skin, then other immunities need to be activated in the body. So Ebolavirus is definitely a virus you don't want to get past the skin. Okay, so for an example for like a chemical barrier of the third immediate innate immunity that I'm going to talk about is the stomach. The stomach actually plays a really important immunological role when it comes to providing protection against pathogens. So chemical barriers such as the stomach play an important role in the immune system. The best example of a chemical barrier in the immediate innate immune system is stomach acid. If a virus gets past the acid mucous membranes in the mouth and the pharynx and the esophagus, right? Because the mouth, pharynx, and esophagus, they have a lot of antimicrobial peptides too. They're more acidic as well. Lots of pathogens actually just die there or can't do anything after getting stuck in the saliva, But let's say, you swallow some food and boom, some food with pathogens ends up in the stomach. Well, there's hydrochloric acid in the stomach, and it plays an important role against these pathogens when ingested with food or water. Hydrochloric acid has a gastric fluid pH of 1 to 2. So that's very, very, very acidic. That's pretty much the most acidic you are going to get. And it is just absolutely destructive to many microbial pathogens. However, the neutralization of gastric acids by like antacids or the inhibition of acid secretion by various drugs, or even like, for example, like if you eat a certain amount of food or drink a certain amount of water, what can actually happen is the stomach becomes less acidic and you have pathogens surviving through the stomach. So like some pathogens get past the stomach and don't die because of hydrochloric acid. So, not every immune response is perfect. That's why there's one immune response and then another one kicks in, another one kicks in. But the problem with EBD, so like the problem with Ebola virus disease is that although it can't survive in this type of environment, usually things like antacids or certain foods or just water, it inhibits the stomach acid's ability to provide that chemical barrier, and it can bypass its immunological properties. Right. So this is probably the most dense thing I'm going to talk about in my presentation here. So probiotics have actually been a relatively new study in immunology and even other fields such as psychology and stuff. So like a lot of psychology professors will talk about the mind-gut connection and the production of serotonin and how it helps with like depression and certain mental disorders or something like that. And they mentioned like good gut bacteria and how it helps disable pathogenic bacteria in the gut. That's why probiotic yogurt's really good, because you fill your what they call a microbiome, right? So we're hearing studies that this is really good for you. And it's a natural way of preventing and overcoming diseases, including bacterial infections, fungal infections, viral infections, cancers, and even autoimmune diseases, and many more. This gut bacteria is also known as what is called the microbiome, like I just said. To expand on that, the gut microbiome, to expand on that, the gut is the key habitat where most of the microbes stay in the host symbiotically. So we have a symbiotic relationship with this bacteria. So they're benefiting us for some reason, they're producing something that we need, whether it's to fight pathogens or just to give us some type of nutrients or to absorb something that whatever it is, we are in a symbiotic relationship with them. So we give them a refuge. They give us nutrients that we need. They help us fight pathogens to survive, right? So, yeah, in the gut, the microbiota, so like the microbes play an indispensable role in maintaining intestinal homeostasis. The gut microbiome includes different microbial communities, not restricting to bacteria, viruses, and fungi. The microbiome is composed of 4 main microscopic organisms in the gut. The 4 main microorganisms or bacteria, they're called, and I'm going to try to pronounce this right, Firmicutes, Bacteroidetes, Proteobacteria, and Actinobacteria. The human body is obviously in a symbiotic relationship with this gut microbiota. There are four main defenses this microbiota provides when it comes to viral infection, which might sound surprising. So, such as the case with the Ebola virus disease. So first, bacteria provides a really hefty amount of mucus immunity in the intestines, right? The mucus, like I was saying, provides antimicrobial peptides that fight against these viral infections. Second, probiotics can induce and enhance other innate and adaptive immune responses, such as the activation of phagocytosis and even through the activation of Bcells in the host body. Third, probiotics are very efficient at raising the host's level of vitamin D. Vitamin D is an important vitamin in the innate and adaptive immune response. Immunomodulatory effects of vitamin D acts on both the innate and adaptive immune systems, thereby reducing risk of infection and fatality. And since probiotics can help regulate and appropriately increase vitamin D in its host organism, viral infections become a lot easier to fight in later stages of the body's immune response. Vitamin D also plays an important role in cellular transport through different types of junctions, while viruses actually, such as the Ebola virus, they try to infect cells by disrupting these junctions, right? Vitamin D fights against these viral effects. Lastly, probiotics actually exert antiviral activity as well, not just antibacterial like we all thought. By actually having a direct probiotic virus interaction and the production of antiviral inhibitory metabolites. So it literally tries to disable certain viruses. This interaction between gut bacteria and Ebola virus is still unclear, but it is fairly obvious that gut bacteria does provide some immunological aid in all infectious diseases to some type of degree. Okay, so the fifth immediate innate immunity I'm going to talk about here is one more antimicrobial peptide that actually it's called LL37. It is a specific antimicrobial peptide that we have, I believe, but not in very high amounts. But it actually helps suppress, and I'm going to point here. So the one that is really good in it at inhibiting. So right here, antimicrobial peptide. We want to inhibit, I believe it's CatB. So it's called cathepsin B mediating processing that this virus does. And pretty much this CatB is really the main cause of Ebola's large suppression of the body's immune response. If you can somehow disrupt that glycoprotein that it produces, you're going to have activation of the adaptive immune system. It's not going to bypass the major histocompatibility complex that I'm going to talk about later. It's going to pretty much your body's going to be able to react to this virus. The main reason that Ebola virus disease is really, really tough to beat is because it suppresses your immune system and it makes certain like interleukins really, really high that causes bleeding and hemorrhaging to be really easy. But some other ones, like it doesn't allow cytokines to be secreted by like dendritic cells and other cells, so it's very hard because it suppresses certain immune responses and then it like overstimulates other immune responses. So like later, I think I'll talk about interleukin 10. It really amplifies that, and that's what causes hemorrhaging and in people, and that's really what causes death because people bleed out from this virus. So to talk about this peptide, so what makes EBD? I'm going to refer to Ebola virus disease as EBD from here on out. So what makes EBD so dangerous, and what can stop it? EBD actually contains a particular protein that causes a human's immune system to either over-respond, like I was talking about, or be suppressed. In a study from PMC Labs, they showed that human cathelicidin antimicrobial peptide, AMP, it's called LL37, as shown on the slides here, and its engineered counterpart, so they can engineer this as well, inhibit the infection of the recombinant virus pseudotype with EBD glycoprotein and the wild type EBD. So the glycoprotein of EBD virus is known to produce cathepsin B mediating processing, a process that is upregulated in many diseases to progress an infection at an enzymatic level. So whatever this glycoprotein does, like we're talking about, it suppresses the immune system, and it is meant to just, this specific one, really, really meant to cause high levels of viral replication, So what LL37 does is it actually inhibits that glycoprotein, like I was talking about earlier, which is good because then macrophages can do their job. Dendritic cells can start doing their job. But lots of times, we have to have large amounts of these to actually make a really big influence. So like artificial LL37 is really important to give a host to maybe help more naturally fight this infection, but it gives them like a boost. It boosts their immune system almost. All right. So for the next 5 activated induced innate immunities, we're going to start with the inflammatory response. So a couple hours go by, right? You don't really know you're infected by now. The body starts to produce, maybe let's say you get a cut in the skin, right? The body starts to produce an inflammatory response to the infection. Mast cells are going to start secreting histamines. Phages, phages are going to start surrounding the area and secrete cytokines, and it's all going to secrete vasodilation, and white blood cells are going to start coming in, and it's this flood of white blood cells and macrophages, and maybe there's dendritic cells there. They may be already there, but what really happens is it leads to the excretion and dissemination of white blood cells to that particular tissue that is damaged. However, some of the Ebola virus disease, EBD, is able to be eliminated from the innate process. Most viral particles of EBD will not be able to be destroyed by normal innate immune responses in white blood cells. just like I said in the last slide, this glycoprotein 1 I mentioned, like the main thing that really can destroy Ebola in someone's body is if the more complicated immune responses are triggered, more of the adaptive immune responses are triggered. It's a very, very tough virus. It's gonna take a high level of immunity. You know, it's very, it's viral replication. You know, it's very high, and it just avoids being killed. It's just very good at avoiding the immune system. So that glycoprotein 1 actually causes, as I was saying before, too much of an inflammatory response in human where it can even be fatal. So like if you get that cut, you know, oh, yep, interleukin 10, IL-10 actually overreacts and stimulates too much vasodilation, even widespread throughout the body. And it can get to a point where, you know, Ebola starts metastasizing to other places really quickly because of this vasodilation. And they like to aggregate in organs. And then NK cells start, you know, attacking its own organs. And then you go into multi-organ failure, then you bleed out. So it's a really rough disease. But yeah, so the second one here is macrophages. So to add on to the inflammatory process in this discussion of macrophages, filoviruses, such as Ebola, primarily replicate in mononuclear phagocytes, inducing production of pro-inflammatory cytokines. This process may explain the damage to the lymphatic organs. So there is so much pro-inflammatory stuff going on with like interleukin 10 that literally your lymphatic organs are getting damaged because there's so much swelling. That's crazy. So although there's not enough cytokines being produced, there's some inflammatory, pro-inflammatory things not being produced, like such as cytokines from like dendritic cells to maybe respond to hold on, they're responding, but what's not happening is they're not producing the MHC complex. Yeah, the MHC, which I'll talk about later. But anyway, so you know, this whole thing where the virus really infects monocytes and macrophages, it's a problem because it leads to a lack of aid in the immunological process. It disrupts the pathway to activate the adaptive immune system. And with increased permeability due to this inflammation, it can lead to the main and most deadly symptom of Ebola virus disease, like I talked about before, hemorrhaging. Digested Ebola virus disease, viral particles are absorbed by the macrophages. Its lysosomal properties causes it to recruit other phagocytes via cytokine excretion, but there is so much cytokine excretion going on. However, there is no MHC showing. Like it's like a perfect storm for the Ebola virus, right? Because now it's recruiting all these macrophages just to devour them, just to infect them. If they're so good at infecting monocytes, such as dendritic cells and macrophages, they're literally tricking the human body's immune system to win. That's what they're doing. So the next immunity is fever. So what does a fever do? Well, there's really not much to a fever except that there's an inflammatory cascade event that takes place from the infection. So you have an inflammatory response, well, you're going to have a fever, probably, right? It's going to trigger the hypothalamus. I believe that's what produces and raises body temperature. to try to make the virus's living conditions uncomfortable, but it doesn't seem to be super effective when it comes to the Ebola virus. I don't know why necessarily, but we know that it is a tough virus. It isn't super clear, but it just doesn't seem to be super effective. But we know there's a response, right? So in most cases of Ebola virus, the fever is a result of exogenous pyrogens that induce the release of endogenous pyrogens, such as interleukin 1. So interleukin 1 causes the fever to be produced. Tumor necrosis factor alpha and interleukin 6 and other cytokines, which then go on to trigger cytokine receptors or of exogenous pyrogens that directly trigger toll-like receptors. All right, so interferons for the fourth one for activated and induced innate immunity when it comes to EBV. This study shows that there are interferon, IFN1, interferon 1 pathways that are activated to act against Ebola virus infection. Cells infected with EBV, either endothelial or epithelial cells, will produce an interferon signal before apoptosis to allow surrounding cells to prepare and to produce microbial defenses, as well as the recruitment and acceleration of white blood cell responses. When interferons reach their destination, they create a domino effect of responses within the cell for the modeling of antimicrobial defense production. This production most notably takes place in dendritic cells during EVD infections, due to EVD's natural design to infect monocytes, specifically macrophages and dendritic cells. Although interferon 1 response helps fight EVD, the earlier this response is produced, the more likely a non-fatal outcome is also produced, because EVD is just such a tough virus. So for example, let's see here. So this actually is a diagram of Ebola right here. Boom, it comes here into an infected cell. This infected cell creates type 1 interferon and produces also pro-inflammatory cytokines. So boom, inflammation is going to be created. It's going to bring over certain macrophages, white blood cells, and the like, right? And then you have type 1, if I get my cursor around here again, type 1 interferon that's going to come around, cause apoptosis in this, and then it's going to go to healthy cells, and antiviral responses are going to take place inside the cell and outside the cell. Okay, so NK cells. In lethal EVD infections, levels of both NK and T cells decline drastically in the circulation and lymphoid tissues before death. So based on that, we can start to infer, okay, well, NK cells must play an important role when it comes to survival with EBD. NK cells possess multiple antiviral properties. They can kill infected cells, secrete inflammatory cytokines, and shape the adaptive response by interacting with dendritic cells. Although the antiviral properties of NK cells are well documented, data obtained in this study indicates that the activity of NK cells can also be detrimental to the host. Why can it also be detrimental to the host, though? Well, NK cells of infected hepatocytes and epithelial cells could actually aggravate liver damage. While NK cells, oh, yep. So NK cells can aggravate liver damage because it can pretty much like overkill infected dendritic cells and macrophages, and it can also dampen the cellular responses against EVD. So pretty much, what do natural killer cells do? Right, their main role is to find an infected cell and destroy the cell. Right, so if you have a large, like a really large viral infection of EVD, and it aggregates in certain organs, if your NK response is too high, it can actually be detrimental to that organ. That's why lots of times with Ebola, you can actually go into multi-organ failure as well. So, um, yeah. So in addition, T cell apoptosis due to improper activation rather than direct killing by NK cells may also be responsible for a decrease in T cell frequency in EVD mice. However, for the most part, if the viral load isn't too high, so if EVD's viral load isn't too high, NK cells will participate in a viral clearance and lead to much better survival outcomes. So how do NK cells work? NK cells respond to cytokines and interferons produced by macrophages. NK cells roam the body until they are activated to produce toxic granules that destroy a pathogen. Um, that destroy a pathogen. Yeah. So pretty much it binds to its receptor here in the infected cell. And if there's no inhibitory receptor like this healthy cell, if it doesn't match that, it will destroy it. So that's how NK cells work. All right. So the last 5 immunities here, we're going to end with the adaptive immunities. So we have the cytotoxic T lymphocytes here. So now onto the adaptive immunity. Cytotoxic T lymphocytes are proposed to be critical for protection for protection from intracellular pathogens such as Ebola virus. However, there have been no demonstrations that protection against Ebola virus is mediated by Ebola virus specific CTL. So CTLs in this case, cytotoxic T lymphocytes. So what does this mean? That there's no evidence that there's actually cytotoxic T lymphocytes that are totally designated for Ebola. However, we do know that some type of CTLs are effective enough to fight Ebola virus. The study recommends that future vaccinations will create an abundance of CTLs to fight Ebola virus. So just to explain the CTL process, through the antigen presenting cell, usually a macrophage or a dendritic cell, the major histocompatibility complex 1 and 2 is usually activated and triggers CTL maturation to provide support against pathogens such as Ebola virus. The problem with this is that Ebola virus heavily infects dendritic cells and macrophages, like we talked about prior, right? Ebola virus really heavily infects dendritic cells and macrophages. So similar to NK cells, CTL cells produce specific cytotoxic particles that destroy an infected cell and its viral particles. So yeah, the whole problem with specifically the Ebolavirus infection is that dendritic cells cannot create its MHCs, its major histocompatibility complex. It can't do it. It stops that immune response. And that is the whole response that allows the activation of the B cell, of the T helper cell, of the cytotoxic T cell. I mean, it is what triggers the adaptive immune response. And so that is why, like, it's important to, like I'm going to talk about in the treatment, it's important to have extra measures to relieve symptoms, to, like probiotics, to just give you that extra immunity boost to be able to fight this virus, because it is just mean. So the second B cell, or the second adaptive immunity I'm going to talk about is B cells, specifically memory B cells, and maybe how it starts to differentiate into plasma cells and certain antibodies. There are many studies I just want to mention before I start talking about their antibodies. There are a plethora of studies that show a plethora of different antibodies that are activated from Ebola virus. Some studies say there's not very many good ones that are created. Other studies say there's a lot of good antibodies that are created. It's just like this slide's going to say that there's not very many, but another one's going to say there's a lot. So just be prepared for that. So they're all really good sources. So B cells. So specifically, the B cell response is probably the most poorly understood response when it comes to the Ebola virus. Like I was saying, studies are kind of all over the place, right? So in particular, it appears that the quality and magnitude of the human B cell response early after the recovery from Ebola virus may be reduced compared to most viral infections. There are some monoclonal antibodies created from survivors of Ebola virus. However, there is only one really good monoclonal antibody that we've been able to create that produces any significant immune responses against the virus. And most other ones are not super helpful, even though they help a little bit. So Ebola-specific memory B cells early in convalescence were low in frequency, and the antibodies they encoded demonstrated poor neutralizing potencies. One neutralizing antibody that protected mice from lethal infections. So scientists gave mice really lethal infections, but also gave them monoclonal antibodies. They injected them with EBOV 237, which is on the PowerPoint slide there. It was identified in the panel of 25 human antibodies isolated. Recognition of the glycan cap epitope recognized by EBOV 237 suggests that this antigenic site should be considered in vaccine design and treatment strategies for Ebola virus. And, I agree with that. They saw that it produced immunological effects. So why would you not want to look into producing vaccinations or being able to provide treatments in monoclonal antibodies when people are infected, So just on the B cell response, B cells are created to fight Ebola virus. An antigen binds to the receptor of a B cell to form clones and eventually form an antibody molecule. When B cells form antibody molecules, they form into either memory B cells, which are B cells that can remain in the bloodstream for years in order to fight off another possible infection, or plasma cells that produce the antibodies to fight the Ebola virus infection, which I'm going to talk about next, the plasma cells. So plasma cells produce powerful, broadly neutralizing antibodies also called BNAbs, in the blood of Ebolavirus survivors. Ebolavirus uses its glycoprotein to attach to cell membranes and initiate infection. Well, in a series of experiments, a team delineated interactions between various forms of viral glycoprotein and 3 of the newly isolated BNAbs that they had. The results provided evidence of multiple mechanisms by which the antibodies inhibit actions of all forms of the glycoprotein, thus preventing infection by halting viral entry into the host cell. The team also determined that one of the BNAbs, EBOV520, recognizes and binds to a portion of the virus glycoprotein in such a way that it even prevents it from interacting with the cell surface protein called NPC1 and initiating the infection cycle. So, boom, this antibody that they found called EBOV520, produced by plasma cells, sounds like it just totally prevents interaction between the cell surface protein, NPC1, and it stops the infection cycle from being initiated. So just on the more biological processes of things, B cells differentiate into these plasma cells to form these neutralizing antibodies. Some of these studies show that there are actually a varied number of neutralizing antibodies, as I talked to you about in the previous slide. Plasma cells are often short-lived. They simply produce antibodies that tag pathogens for destruction, and they also disable them. That's very important. So not only do antibodies tag viruses for destruction by a macrophage, but they also disable the virus from even being able to affect any kind of monocyte that comes and destroys them. So that's kind of cool. So dendritic cells. So according to one study, dendritic cells, otherwise known as DCs, I'm going to refer to it as DCs, play a hard role in proliferation and the activation of other adaptive immune responses. In infected DCs, Ebolavirus replicates efficiently and inhibits maturation without inducing cytokine expression, leading to impaired T cell proliferation. However, the underlying mechanism remains unclear. In this study, they reported that Ebolavirus VP35 impairs the maturation of a mouse's DCs. When expressed in mouse immature DCs, Ebolavirus VP35 prevents virus-stimulated expression of CD40, CD80, CD86, and major histocompatibility class 2. While some interferon 1 cytokines are produced, this dendritic cell response happens at a very slow rate, if any at all. CD4 helper cells cannot begin to respond or proliferate until activated by MHC2. So pretty much this study was just saying that, like, yeah, so adding a little bit of DCs into maybe a mouse would help a little bit, but the Ebola virus just pretty much significantly just cuts DC's ability to even present an antigen to continue to create that cascade event to activate other adaptive immunities. And again, that's very bad for its host. Dendritic cells, again, they're produced by monocytes, and they're a main contributing antigen for, presenting. They are super important to increase your chances of survival, to be able to fight off this really, really tough virus. Lastly, we're at the T helper cells. and adaptive immunity. So this is kind of similar to the cytotoxic T cell, right? So like as noted in the previous slide, the inactivation of monocytes, dendritic cells, causes severe lack of MHC1 and 2 complexes, which are extremely vital in fighting viral infections such as Ebola virus. The main way T helper cells are activated in a patient with Ebola virus is through viral load, really. For example, T cell responses, whether CD4 or CD8, are higher in patients with post-Ebola syndrome, also known as PES. It turns out that the longer a person is alive and exposed to a high content of antigens, the CD4 and CD8 cell response will be much higher, which of course that makes sense, right? It makes sense that there's going to be much higher CD4 and CD8 response in people who might be infected longer or who might show a higher viral load or something, right? However, there are some survivors that don't even hardly show any CD4 or CD8 T cell responses, which is weird. So like maybe their viral load was just really low and their innate immune responses, such as like their like antimicrobial peptides, maybe they really helped decrease the viral load, and it maybe the infection just didn't spread like some other people's. So to recap, essentially, MHC class 2 is what triggers the adaptive immune response of T helper cells. They go on to proliferate and produce cytokines to bring CD8 cells to those areas to lysis the Ebola virus. Once again, Ebola virus is very good at suppressing the immune system by blocking our immune system's ability to even present antigens to create an effective adaptive immune response. Oftentimes, it takes a large viral load for this to begin to happen, and treatments increase patient survivability during that time. Which brings me to my last slide here. So for treatments, we have two main things when it comes to monoclonal antibodies and then supportive care. So for therapeutics, there's two approved drugs. There's imazib and ibanga. So the first drug, imazib, was approved in October 2020. It is a combination of 3 monoclonal antibodies. The second drug is ibanga, and it's a single monoclonal antibody, and it was approved in December 2020. So essentially, monoclonal antibodies, also abbreviated as MABs, are proteins produced in a lab or other manufacturing facilities that act as natural antibodies. So pretty much they go in and they extract a certain antibody that an organism created, and they just clone it and clone it and clone it. So it comes in large amounts so they can give people these treatments through IV, through shots, however they do it. But pretty much these MABs deactivate and interject the Ebola's glycoprotein, which is the whole, it's the whole thing that causes that whole terrible event of infecting the dendritic cells and not allowing it to produce an MHC complex. By blocking that glycoprotein, it doesn't even allow the Ebola virus to even enter someone's cells. So these treatments are actually approved by the FDA, and it's the only known treatment to actually be effective against the Zaire Ebola virus. So that's pretty cool. Other than that, early intervention is the best way to really ensure survival when it comes to Ebola virus. The most helpful thing is to just someone's just got to go through the process. They just have to kick the virus, right? You can give therapeutics, you can give supportive care. That is going to be the best way for someone to survive this virus, is to give them fluids. They're going to go through dry and wet symptoms. Keep them hydrated, keep them, keep their electrolytes balanced. When provided early, using medications to treat their vomiting, to treat their diarrhea, to treat their headaches and pain, fever, and blood pressure, or give them maybe vasoconstrictors, just something to keep their symptoms at bay so they don't have like super big hemorrhaging, because it's going to hit them hard, But that's it. That's the end of my presentation. It went a little longer than I thought, but I have a lot of information. I wrote about 18 pages of stuff. So, yep, my references are going to be in Canvas if you want to look at that. And so is my script. But thanks for watching.